Thanks, John. So yeah, I'm going to talk about some studies that we've done in rapidly rotating convection in both plane layer, QG, and as well as spherical shell geometry. And a lot of the work here was carried out by these two very bright, very hardworking grad students, Tobias Oliver and Justin Nikoski. And of course, a lot of this work was done with Keith, mainly this one here. So I'm going to talk about these two studies primarily. Interestingly, funny story, met Keith here at IPAM in 2010, maybe? 2009. And there were some big personalities in the room. And he was giving a talk on rotating convection, the QG stuff. And there was someone in the room, a well-known person, I won't tell you their name, and they started lecturing Keith on non-hydrostatic QG theory. And I was sitting in the back and I just, thought this was pretty funny, amusing. Even when you're probably the world's leading expert on something, there's probably someone in the room that thinks they know more than you do. So anyway, and on top of that, what's interesting is that Keith and Edgar and I think it's Julian, Knobloch, Millif, Warren, JFM 2006 have this beautiful paper where they show the relationship between large aspect ratio QG and small aspect ratio QG. So I think that Keith had already demonstrated his knowledge of QG theory by that time. Anyhow, so I'll talk about some of the results from this study, as well as another one that came out in 2024, where we're looking at the asymptotic behavior in rotating spherical shells. So with that, back to the familiar, simple world of linear theory, which many people have talked about. But I want to talk about a few specific things that I think are helpful for framing the discussion that I'll have here. So most of us are familiar with the linear theory of rapidly rotating convection. This is detailed in Chandrasekhar's book. And so if you look at the linearized form of the governing equations for rotating convection, and you're interested in the marginal state of convection, this is the Rayleigh number that satisfies that marginal state. Okay, here's the wave number, the horizontal wave number of the system. And this is just linear theory for planar convection. And on the plot, I'm showing Rayleigh versus wave number for a couple different Ekman numbers. So a rather large Ekman number down here. And you can see the peak is below 10. And as the Ekman number is reduced from 10 to the minus 2 to 10 to the minus 6, you can see this well-known shift of the minimum up to higher wave number. And a couple other features associated with this are that this kind of high wave number branch scales like k to the 4, k to the power of 4, and this branch scales like k to the minus 2. So it's well known that the most unstable mode is selected by the viscous force. And because of that, the viscous force perturbs the leading order force balance. You get this particular asymptotic scaling behavior for the critical wave number. In addition, the critical Rayleigh number, it's well known now that the critical Rayleigh number scales like Ekman to the minus 4/3, and so it's convenient to rescale the Rayleigh number in this way. You take Rayleigh multiplied by Ekman to the 4/3, and you get asymptotically a parameter that's order 1. And if you replot that data, so this is the same data, just on axes that have been rescaled with these asymptotic scaling behavior. And so, again, there's nothing new here, but this is just multiplied by that. So this is reduced Rayleigh, and this is a reduced wave number. And so in this parameter space, these rescaled coordinates, it's nice because everything becomes order 1. The Rayleigh number is order 1. Now, and the wave number is order 1. The peak here is about 1.3, and the critical wave Rayleigh number is about 8.7, and this has been mentioned a few times. What I wanted to emphasize, however, was that it's not just the critical wave number on this branch, on this curve, that scales like Ekman to the minus 1/3. It's the entire range that scales like Ekman to the 1/3 in the rapidly rotating limit. And so I've plotted this scaling behavior here on this, it's the solid line. You can't actually make out the difference between that and the 10 to the minus 6 Ekman number scaling. So in other words, all of these wave numbers in here, inside this unstable region on the marginal curve, are scaling like Ekman to the minus 1/3, not just the minimum. And this is important, I think, with regards to interpreting the asymptotic theory. So I'm going to talk just briefly about the stuff that Keith and Edgar and others have worked on to develop this model. Just a couple things that, again, are helpful for interpreting the results of the simulations. So if you're not familiar with this, in the limit of rapid rotation at small Rossby, small Ekman, you get a geostrophic balance at leading order. Looks something like this. And then the system is perturbative, it's quasi-geostrophic, and so if you carry out this asymptotic expansion as they did, just kind of summarizing what you'd get here. Of course, there's a lot of details swept under the rug here, but you would get something like this. You get a prognostic evolution equation for the dynamics, where everything enters at this order, including viscosity and buoyancy and inertia. And of course, you would, as shown in their papers, you would impose solvability, and you derive two scalar equations from this three-component momentum equation. So the system's reduced. And what I want to emphasize with regards to what I'm going to discuss are the scalings for these various quantities. The velocity field U here scales like Ekman to the minus 1/3 in my non-dimensionalization. So I'm choosing the depth of the domain. The large scale is my length scale. And so with that, these are the scalings that I get. And so the temperature perturbation is small. It scales like Ekman to the 1/3. And the length scales scale like Ekman to the 1/3 as well. And what I want to emphasize is that you can't get away from these scalings. They persist in the nonlinear turbulent regime. They are a fundamental feature of the dynamics, and they are independent of geometry. Whether you're in a sphere or a plane layer, these scalings all pop out. Okay, so those are the scalings with Ekman, and of course, we'd like to understand how these things scale with the Rayleigh number, right? Linear theory can't tell us that because it's independent of the amplitude of the convection. So it's a well-known way to estimate this is using what's called a CIA, Coriolis Inertia Archimedean Balance. So you go into the governing equations and you balance these different terms, and you would come out with this sort of scaling for the flow speeds and the length scale in the system. And this is pretty well known. So this translates in asymptotics land to a reduced Reynolds number, a rescaled Reynolds number that goes like reduced Rayleigh over Prandtl. And the thing that I want to emphasize, and that John Arno mentioned yesterday in his talk, is that there's this Ekman to the 1/3 factor that's still sitting there in front of your length scale. So the length scale goes like Ekman to the 1/3, but it also has this Rayleigh number dependence built in here. And so we're kind of interested in testing this. So I want to talk a little bit about previous work that Keith and collaborators have done, because it kind of sets the stage for the stuff that we've done more recently. And so back in 2012, Keith and coworkers published this PRL paper. And they are showing here a plot of the Nusselt number versus reduced Rayleigh number. This is a compensated plot. So this is compensated by that Rayleigh to the 3/2 power, which is often referred to as a diffusion-free type scaling for the heat transport. And so the plot shows this compensated Nusselt as a function of reduced Rayleigh for a wide range of different Prandtl numbers. Anything greater than 1's shown in gray, so these are higher Prandtl numbers. And then the results are indicating that this compensated value is becoming flat as the Prandtl number is reduced and the system becomes more turbulent. And they also have this in another paper, the GFD 2012 paper, where they plot RMS flow speeds multiplied by sigma, which is just the Prandtl number here. And so they're showing basically a reduced Reynolds number versus reduced Rayleigh number. And they have this slope of 5/8. And so we were kind of interested in understanding if that is consistent with CIA balance in the governing equations and whether this persists for a range of different Prandtl numbers as well. The other fun thing they found was that when you do these simulations, there's a condensate in the system, so there's an inverse kinetic energy cascade. If the flow is turbulent enough, you generate these large-scale vortices, and you can kind of see them floating in here like this, and I have some movies here too. And so one of the other things that we were interested in understanding was how these large-scale vortices are impacting the scaling of global transport quantities as well as balances in the system. These are simulations of the reduced model at a reduced Rayleigh number of 40 for a Prandtl number of 1. So this is a top-down view, a perspective view. At Prandtl 1, the large-scale vortex dominates the kinetic energy at this reduced Rayleigh number. In fact, it becomes dominant around a reduced Rayleigh number of 25 or so for Prandtl 1. So it quickly becomes the dominant, energetically dominant mode in the system. And this is a higher Rayleigh number, so it's reduced Rayleigh 200, and you can see how strong that large-scale vortex is relative to everything else. Okay, so Stefano Maffei carried out a broad suite of simulations for this reduced model in order to look at how that large-scale vortex was influencing the scaling of these various quantities. And the thing I should mention is that once you have these large-scale vortices in the system, it takes an incredibly long time for these things to saturate. And so you have to carry out these simulations for a long time, which he did over a broad range of different Prandtl numbers. And so here he is plotting the reduced Reynolds, rescaled by that diffusion-free CIA scaling. So it's a compensated plot. And you can see that at the lowest Prandtl number, the behavior is that it kind of bends over at a particular reduced Rayleigh number, and then it kind of deviates from that diffusion-free scaling. There is a certain range, depending on the Prandtl number, where it looks like it might work, and then it deviates once the large-scale vortex becomes dominant. So we wanted to understand this behavior. And so one of the things that Tobias Oliver worked on in this paper was the following. He said, well, if the large-scale vortex is influencing the scaling behavior of these things, maybe it would be helpful to just eliminate it altogether, right? And there are ways that physically motivated ways you could think about how to do this. For instance, you could have Ekman pumping, something like that damps the large-scale flow. However, even with Ekman pumping, the large-scale dipolar vortex dominates the kinetic energy. So even its very small Ekman number. So we came up with a little trick in order to remove it. And so this is showing you the vorticity equation for the system. So this is zeta. Here's the vertical component of the vorticity vector. It's the Jacobian, vortex stretching, and diffusion. And now, if you depth average this equation, and we're denoting a depth average with the angled brackets, then you would get an evolution equation for the depth averaged vorticity in in the system. And that turns out to be the energetically dominant feature in this system. So we said, okay, what if we add a term into the equation such that when you depth average it, it removes that component of the flow? And so if you set gamma equal to 1 and you depth average this equation, then you just get a nice simple diffusion equation. And so we're basically taking energy out of the large-scale vortex so we don't have this large swirling motion, et cetera, to influence the scaling behavior in the system. And so Tobias did that, and this is an example of what happens when you do this. So this is a plot showing the kinetic energy as a function of time in a typical simulation. The blue data points are showing the standard QG simulations with gamma equal to 0. So the large-scale vortex is present in that system, and it's saturated. So up here, this is showing the depth average kinetic energy, so the energy contained in the depth average flow. Down here is showing you the vertical component of the kinetic energy. And oops, if you turn gamma to 1, set gamma to 1, immediately you see that the large-scale vortex decays exponentially with time, as you would predict from a simple 2D diffusion equation. And so it gets the job done. So Tobias did a range of simulations with this system. And so some of the results from this study, this is a plot showing the compensated Nusselt number as a function of reduced Rayleigh number. And so the red data points are showing the results where we've removed this depth averaged large-scale vortex from the system. And then the blue triangles are showing the full system where the large-scale vortex is present. And one of the things, so, it's helpful to remove this just from the standpoint of trying to simplify the system and understand how the large-scale vortex influences the scaling. It also results in numerical savings. You don't have to simulate for quite so long. And so this allowed him to push the parameter range up to about reduced Rayleigh of 280 here. And so what you see here is that there is some correspondence between the no LSV and the LSV case for low Rayleigh number, where we'd expect it to work, where the large-scale vortex may not play such an important role. And then when you have the LSV, you see this kind of slight deviation from this diffusion-free scaling. And when you remove it, you also see a slight deviation. There might be a little asymptotic behavior here at higher Rayleigh number, but it's not completely obvious. And this is a plot showing the reduced Reynolds number, compensated by that diffusion scaling as well. And so you can see that the case with an LSV never really approaches that. It never really flattens out. And at best, maybe these highest Rayleigh number cases are flattening out here. And then the open symbols are just showing the compensated value that you would need in order to flatten it. So they have a slightly stronger scaling than a power of 1, which you would expect from a diffusion-free scaling. Length scales. So Tobias computed a variety of different length scales from these simulations. And this is a plot showing all of these length scales normalized by the critical horizontal wavelength. So a value of 1 you would observe right at the onset of convection. As a function of reduced Rayleigh number, I just want to focus on these two quantities, these two length scales. So the magenta data points are showing the integral length scale, and the green triangles are showing you the Taylor microscale, so a viscous dissipation scale. And you can see how the integral scale does show an increase with reduced Rayleigh number, but it's not following the diffusion-free scaling, in fact.
How do you define those, though?
How do I define?
How are you defining integral? How are you defining Taylor? What are you doing exactly?
The integral scale is just an autocorrelation length, and then the Taylor microscale.
It's K times the spectra. So
Yeah.
K over
but it's the same as an autocorrelation, yeah. And then the Taylor microscale is just computed in the standard way. Does that answer your question, John? Do you want me to show you the relationship?
It's just helpful, but you can just say what it is.
So it's also, so the reason I presented the marginal stability data is because you can also look at these length scales relative to those curves. So Tobias did that. So this is a plot showing you the reduced Rayleigh number as a function of the wave number in the system. And you can see all the different length scales that are present. And so this dot dashed curve is just showing you the marginal stability behavior. And what you see is that the integral length scale, the magenta, and the Taylor microscale, they're all within this envelope that's bounded by the marginal stability curve. Right? So it's essentially telling us that these length scales all remain comparable to the critical horizontal wavelength in the system. In other words, viscosity continues to play a role even at very high Rayleigh number for the system. The red data points are this red curve. These are the fastest growing modes for a single wave number. So take linear theory and assume a specific background temperature gradient. You can compute growth rates, and you can find the wave number that produces the fastest growing mode, and that's shown here just for comparison. And it has a scaling that goes like k to the minus 8. Okay. So the conclusion from all this is that these length scales remain within the viscous range for rapidly rotating convection. And these are the most extreme simulations done to date with this model. So if we can't rule out that it transitions at a higher Rayleigh number, but so far all these length scales are remaining comparable to that viscous scale. Okay, so what do these flows look like? This is a plot showing you the axial component of the vorticity for a range of different simulations. So this top row here is showing you the vorticity at the midplane, and the bottom row is showing you the vorticity within the thermal boundary layer. So just at a different depth. And you can see how you just get smaller and smaller scale features. And then for comparison, we're showing all the different computed length scales. So the integral scale is shown here in top, right? And it has a slow increase. And then as we're also showing here, the integral scale for the temperature field and the Kolmogorov length scale. If you look at it in the temperature field, it's a little bit more clear what that integral length scale might mean. Yeah.
I'm a bit confused when you say that this integral length scale is like in the viscous range, because it looks, I mean, like the ones on the right, if I think of like a viscous scale, it seems really small, and the integral scale is many times larger.
Right, so I think, let's see. This is why I mentioned the marginal curve earlier. So all these length scales in the within the band of unstable wavelengths that are defined by the marginal curve are influenced by viscosity. That's all I'm saying. And so these length scales remain comparable to that. So if you look at this plot, it's normalized by the viscous length scales, 1 here, right? And we get 1, 2, 3. We get up to about 3.
Sorry, you're normalizing to what?
By the horizontal critical wavelength. Does that make sense? So at the onset, the only scale present in the system is 1 scale. Okay. Temperature seems to show larger scale structures.
Can I ask another question?
No,
If we go back
you
to that.
can't.
If we go back to that.
Please interrupt.
So you also had L, proportional to the square root of Rayleigh tilde over Prandtl times Ekman to the 1/3. Does
Yep.
that also explain this? If we further reduce using that square root of Rayleigh tilde does that,
No, these length scales are not following a scaling that strong.
okay,
Yes,
so they're even closer to the onset scales?
yes, yeah.
Okay.
All right. And so, looking at the vorticity field, it's not immediately obvious what these integral length scales correspond to in physical space, but it might be a little bit clearer in the temperature field. Oops. Where, the integral length scale is shown here, and that kind of looks like maybe it's comparable to these eddies that you see here. Maybe this is the integral scale, et cetera. Yeah, do you have a question, Daniel?
So, if I understand correctly, you're saying that the kind of like the large scales that we're seeing here, it's say like 3 times larger than the unstable mode at
Yep.
onset.
Yes.
When the viscosity was way larger.
No.
No.
No, viscosity is not changing. Is that what you're saying?
Because I guess is the size of the is the size of the domain here fixed with respect to the viscous length?
Yes. Each box is, in these simulations, it has 10 unstable wavelengths in horizontal.
Okay. Okay. Maybe we can chat afterwards.
Sure. Okay, so the other thing that we looked at, that Tobias looked at, was what are the observed balances in these governing equations? So you take the reduced asymptotic model, and you can compute RMS values for all the different terms in the governing equations. And so here I'm showing the RMS values as a function of depth in the domain here. And so I cut off the axes, unfortunately, but this is 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. And it's on a log scale so that you can see the thermal boundary layer behavior as well. And so what you see there is that, as you expect, inertia does play a dominant role at high Rayleigh number. However, one of the interesting things is that the buoyancy force, it scales in such a way that it becomes comparable to the viscous force in the interior. And the only part of the flow field, the domain where it remains kind of a dominant feature, is right at the thermal boundary layer. And in fact, if you look at the ratio of these forces as a function of reduced Rayleigh number, what you find is that these two forces become closer and closer together as the reduced Rayleigh number is increased. So the black dots are showing the ratio of the viscous force to the buoyancy force as a function of reduced Rayleigh, and you can see that this curve just keeps going up and up. One reason for why that might be the case is because in rotating convection, the interior temperature gradient saturates. And so the heat transport is controlled by the interior. And so that might be an explanation for why we observe this behavior. So those are results from plane layer QG simulations, and I'm going to switch gears here into spherical geometries. And long story short, you observe very similar behavior in the sphere. So here's our setup, and these results are all summarized here. We have a rotating spherical shell, hot interior, cooled exterior. We also use stress-free boundary conditions because we're also interested in understanding the amplitude of the zonal flows that you get in this system and how those scale with our input parameters.
Hey, Mike, sorry, I'm going to ask a really naive.
Go ahead.
Does QG imply Boost?
Does QG imply Boost? No, you can have
So this is stratified, or
the spherical stuff.
maybe it could be.
Everything I'm presenting here is Boost-esque.
Okay,
Yeah.
that was my question. Thank you.
So we have our standard set of non-dimensional parameters. Ekman, reduced Rayleigh. We're going to show everything as a function of reduced Rayleigh. And Justin carried out a broad suite of direct numerical simulations in a sphere. So what does the flow look like? In a spherical shell with stress-free boundaries, what happens is that you get different force balances depending on what scale of motion you're interested in. And so I'm going to decompose the flow, all flow quantities, into an axisymmetric component, so a zonal average. So the bar here is just a zonal average. And then everything else, the primed quantities, I'll just call the convection. And so this is a plot showing you the typical structure, and this has been studied in detail before. So this is an equatorial plane view looking down on the rotation axis. This is a meridional view of the convected structure. Zonal flows look something like this. So in this particular aspect ratio, you just have one big prograde jet, so red, orange, positive, flowing into the page. Blue is coming out of the page, and this is pretty typical. It's well observed in previous studies. This is kind of showing you what the dynamics look like in this system. So this is an equatorial plane view of the radial velocity. And this is a plot of the convective Reynolds number as a function of time. And so the little red dot there is showing you the timestamp on each frame from the movie. And you get these kind of relaxation oscillation type dynamics in this system. You get a feedback between transfer of energy between the convection and the zonal flow in the system. So kind of dramatic behavior here.
What's real?
Rayleigh tilde for this case, I think is 60, maybe? Yeah. So coming back to scalings. So we're going to scale the heck out of all this data and show that all these scalings work in the sphere. So this is a plot of the convective Reynolds number as a function of reduced Rayleigh for all these different simulations. So this is Ekman 10 to the minus 4 or 10 to the minus 3. 10 to the minus 3, and then as Ekman's reduced, you move up and to the left here. Okay, so the stars are our smallest Ekman number. If you rescale that, if you have a geostrophic force balance on a viscous length scale, you would expect that the convective Reynolds number scales like Ekman to the minus 1/3. So if you take all that data and you rescale it, so this is the rescaled Reynolds number, not surprising perhaps that all this data kind of collapses to a line, which means that you're in this asymptotic state for the dynamics. The open symbols are just a different aspect ratio, so a smaller depth on the shell. Zonal flow speeds. So the zonal flow speeds in the system tend to be a lot larger, but they're governed by different dynamics. So in this system, with stress-free boundaries, no magnetic field, et cetera, the zonal flow is geostrophically balanced too, just like the convection. And what that means is that the only way to damp the motions is to use viscosity. And so if you look at the zonal component of the momentum equation, the only balance that can occur is a balance between viscous stresses and the divergence of the Reynolds stresses. And so if you know how the divergence of the Reynolds stresses scale, which we do from the small scale convection, then you can predict how the zonal flow scales with Ekman for these simulations. And so it has a much stronger scaling on the Ekman number, Ekman to the minus 2/3. And so this is a plot showing you that reduced zonal Reynolds number as a function of reduced Rayleigh number. And it does a pretty good job. Yeah.
Do you get to high enough RA here that you went above ROC1 and that the flow reversed at the equator, or are these all prograde?
No, we did not go into a high Rossby number regime. Yeah. Some of these simulations are definitely on the edge of that, but no, we didn't cross that boundary. Yeah.
Why didn't you use large-scale drag to dump your zonal jets?
Why didn't we use large-scale drag to damp the zonal jets? Primarily because we're interested in the limit where that drag goes to 0. to understand the maximum amplitudes that that flow can have.
But it might be physical mechanism which you just throw it away.
Absolutely, sure. Yep.
All right.
Yeah.
Sorry. What happened to the circulation in the zonal force balance? Why doesn't the circulation play a role? You said viscosity.
Oh,
and
from the
metals.
zonally average Coriolis force? Is that what you mean?
Yeah, I guess it would show up.
It's just weak.
Okay.
Yeah, it's there, but it's small. Yep. Okay. So we kind of did the same thing with the sphere. We went hog wild with all the length scales we could possibly compute in order to see how they scaled. So Taylor microscale. This is the dissipation scale. John, it's the square root of the kinetic energy divided by the viscous dissipation rate. Okay. This is small Ekman number, so you can see that there is a very obvious trend of the Taylor microscale going down, becoming smaller, and you would expect that this would go like Ekman to the 1/3. Sure enough, if you take the data, rescale it with Ekman to minus 1/3, it all collapses. It doesn't scale with Rayleigh in quite the same way as the plane layer. We don't understand all that, but the collapse is encouraging. Similarly, you can compute length scales incorporating other components, other parts of the kinetic energy spectra. So this is kind of akin to an integral length scale here. And so same data, same range of Ekman numbers. You can collapse it with Ekman to the minus 1/3 pretty well. Okay, so once you rescale these quantities, they become order 1, indicating that this scaling is consistent.
What is this quantity?
This is like an integral length scale.
It's an integral length scale.
You can't define it in quite the same way in spherical harmonic space as you can for the Fourier. Yeah, it's like a weighted average of the kinetic energy spectrum now.
Weighted by L.
Yes.
Okay.
Yep. Does that make sense?
Yep.
Okay.
Physically, it looks like it's asymptoting to 3-ish.
Yeah.
Is there a physical interpretation of why that would be, what that means?
I don't know.
Yeah.
Yeah. Do you have an idea, John?
No. No, but you're giving me time to talk.
I haven't thought about everything, John. All right. The really nifty thing, too, is that, you can take all the forces from the governing equations and all the theory from the plane layer and apply it to the sphere to figure out how all these terms scale, and they all scale identically to the plane layer. So this is showing you RMS values for the buoyancy force in a spherical geometry as a function of, I lost my Rayleigh number, as a function of reduced Rayleigh number. It should scale asymptotically like 1 over Ekman, so if you normalize that, you get this nice collapse of all the data. The inertial terms should also scale the same way as the buoyancy force, as well as the viscous force, which I'm not going to show. But here's the inertial term, rescaled, and you get a nice collapse. So it's indeed in this asymptotic state. And then I mentioned the ratio of the viscous force to the buoyancy force from Tobias's QG simulations. This is the same ratio from the spherical simulations. And because these forces scale the same asymptotically, when you take their ratio, it better be order 1. And so indeed, it is order 1. It doesn't quite hit values of order unity. That might just be a geometrical issue, but they do scale the same way. You still see this state where the viscous force is becoming more important with increasing Rayleigh number. Oh, okay, related work. So just talked about the stuff that we've done, so I want to try to draw a connection with some of the previous work that's been done. This is a paper from Céline Guervy, Philippe Cardon, and Nat Schaefer from 2019. And so the plot here is showing you the length scale that they computed as a function of the Rossby number. That's the output Rossby, by the way. And they carried out kind of a huge set of simulations from, a range of different models. So they have QG, which in this domain just means that they assume that the flows are actually invariant in the system. And so it's essentially a 2D problem. They also have, 3D data in here as well. And what they're showing in the inset is this length scale compensated by Rossby to the 1/2. And so this is that diffusion-free scaling. And you can see as the Ekman numbers reduce that it might be approaching that diffusion-free scaling regime up there. So I want to talk a little bit about what this data means in terms of what the stuff we've done. Are you going to ask a hard question again? About integral length scales?
What is L?
What is L? It is also an autocorrelation
Okay.
length. Yep. Tobias, do you
The
disagree?
spectral peak in this?
I believe in this is not spectral peak. This is an actual autocorrelation computation, I believe. And I think, to be honest, they computed it a few different ways, and they find similar scaling for the different ways that they've computed it, from what I remember.
Just want to know what's being plotted.
What?
I want to know what's being plotted.
A length scale versus a Rossby number,
Okay. So is it like a viscous length or, right?
an integral length scale.
Okay, yeah. Got it. Thanks.
Okay, so I was curious how this data compares with what we have found, and it turns out their data you can get from their paper, and so they have nice tables and stuff like that. So I just grabbed their data, and so there's some subtleties here, and one of them is that they're at low Prandtl number, very low Prandtl number for some of the simulations, I think 10 to the minus 2, and so in that limit, small Prandtl, small Ekman, the convection's subcritical. And so I had to kind of play with the data a little bit. So what I did is I plotted their length scales here. And this is just taken from their spreadsheet. So these are all the length scales for the different Ekman number. And all I did is I took the Rayleigh number and I normalized it by the minimum Rayleigh number, just so you could see all the different data together, just normalized. And then if you take the data and you multiply it by Ekman to the minus 1/3, you get this sort of scaling behavior shown here, which I thought was kind of interesting. The larger Ekman numbers shown here in the gray, it's kind of sitting down here, and then this is also larger Ekman numbers. So then I filtered it, and I said, well, let me just focus on this smallest Ekman number data, which they show here. So that's a plot showing just those 4 smallest Ekman numbers. And you can see that if you take their data and you simply multiply it by this asymptotic scaling, boom, you get all this good collapse of the length scales, which indicates that you cannot get away from this Ekman to the 1/3 scale. It's still present in the system. And then I furthermore compensated it by a reduced Rayleigh sort of 1/2, and you get this sort of scaling behavior. Now, the interesting thing is they also have kinetic energy spectra. So I grabbed their kinetic energy spectra. So I believe the ones with the strong peaks are computed from the radial kinetic energy spectra. And so I grabbed these plots, grabbed these data. Again, this is all available online. And I plotted it here. So all the different Ekman numbers. You see there's a strong peak, and it shifts downward to the right. Higher wave number is Ekman numbers reduced. If you just take that wave number axis there and you compensate it by Ekman to the 1/3 and you normalize it just so you can see them all together, then you get this nice collapse of the spectra, indicating that it's not just a single length scale in the system that scales like Ekman to the 1/3. It's all the length scales that are present in the system. They all scale like Ekman to the 1/3. So you can't get away from this. And then another study carried out by Rudy and his group, Madoni et al., they see some results that are similar to what we found as well in the asymptotic model. So they have a bunch of different length scales. So I'll just focus on, let's see, this one. This is an integral length scale, Daniel. This is a dissipation length scale down here. And you can see that their dissipation length scale is also approximately constant with Rayleigh number. And that's consistent with what we find in the QG simulations. You should contrast this with non-rotating Rayleigh-Bernard convection, where if you compute a viscous dissipation length scale, it has a very strong dependence on Rayleigh number. It scales inversely with Rayleigh. So it goes down immediately right after the onset of convection. And then they have their integral scale, and it has kind of this Rayleigh to the 0.38 power, so something a little weaker than Rayleigh to the 1/2, but nevertheless, it's increasing. Okay, so that's it. Summarize. I hope I've convinced you that the viscous length scale, no matter how you compute it, is present in the system. You can't get away from it, and we see it in all these different geometries. John's giving me a confusing look. And so, if you had to make an estimate for flow speeds, length scales, et cetera, these diffusion-free scalings, they would probably give you an answer that is close to what is actually observed. However, if you go into the numerics and you compute balances, et cetera, it's not really obvious why we're observing that. We don't see, say, a CIA balance in the simulations. And as I mentioned before, we think that the importance of the viscous force, this is probably just a feature that's intrinsic to rotating convection because the interior controls the heat transport in the system. The spherical data that I presented, the main point there is just that the asymptotic scalings that you get there are all consistent with what you would expect from plane layer. There are little caveats, a few caveats that I didn't mention. But the zonal flow, it shows this kind of extreme dependence on the Ekman number. It's also influenced or constrained by viscosity to some degree. Thank you.